Right, so we've had a look at what natural selection is and how it works. We've had a look at what selective breeding is and very, very briefly how that works to create new breeds. What we want to look at now is what they have in common, what's different about them, and are they really actually all that different, or are they just examples of the same thing? So what's the most obvious thing they both have in common?
They both start off with random mutations.
Great. So they're both relying on random mutations. In what process?
Meiosis.
In meiosis. Why is it important that it's in meiosis? What does that mean about the mutations?
That there's variation and keep moving.
It does mean there's variation. The mutations are giving us variation, but the fact that it's in meiosis, what does that mean about why is that so important for both of these processes?
It can be passed on.
Great. So the offspring will have those changes, those new alleles. Okay, so that's important for both of them because that creates what does that do to the populations? What does that do to the populations? Having these random mutations in meiosis happening.
Variation.
Variation, fantastic. So both of these processes rely on variation within a population. If that variation is not there, neither of these processes are going to work. Okay. Is there anything else anywhere in them that is very, very similar or the same?
They still have a pressure
There's some sort of pressure that changes
that drives the change.
So it changes the makeup of the population. The population ends up having different phenotypes shown or different alleles being expressed is another way to put it. Okay. And ultimately, both end up with potentially different
Offspring.
breeds. Okay? You could even argue maybe even new species. So they both have that happening. Okay. Are there any other similarities that you can see that we haven't mentioned there? No? Okay. What about differences? What are the big differences that you can see between them?
Selective breeding is inbreeding and natural selection isn't.
Correct, although there will be some inbreeding in here as well, of course, especially if the population is small. But you're right, that's exclusively inbreeding to start with, and that's not exclusively inbreeding to start with. Good, so that's one difference that might lead to another important difference.
In selective breeding, the human is driving the change rather than in natural selection, it's environmental pressures.
Fantastic, really succinctly put. What does that mean? What's the importance of that though? That's a good observation. What is the importance of that for the offspring in particular, or the population?
Oh, there'll be all positive mutations for environmentally pressure because it's trying to make a more successful offspring. But from selective breeding, which will be about what the human wants, it might not be the best for its species.
Fantastic. It's a really good place to start with. So if I come over to natural selection and pick what was said there, what was said is only positive. It's not quite right. Positive and neutral phenotypes will be maintained here, but negative ones won't. Why would negative ones not be maintained through natural selection?
Because those carriers won't breed and produce offspring that will successfully reproduce again.
Fantastic. And they may even die before they even get to the reproducing age. Very good description. Very good argument. So, if the environment causes the population to change, then generally, as we've said, only the positive, and I've also thrown there, and the neutral mutations are going to be maintained in the population. Whereas what was said over here, and we'll go to this one, this is a really good point. In selective breeding, sometimes negative mutations will be maintained. Think of the ridge on a ridgeback dog. Humans selectively breed for that, and yet it actually is a disadvantage in nature to have that ridge. It's due to a disease in the spine, a genetic disease in the spine. There's dogs whose brains don't fit in their heads because we think they look nice, but they're in pain from about the age of 2 until they die. So we actually sometimes pick negative ones. Or even if we're not picking them, then how could a negative characteristic stay in a population or in a breed or in a pedigree here? that wouldn't stay in here because nature would get rid of it. How does selective breeding also allow these negative or potentially negative alleles to be expressed?
Because we're breeding like certain traits that aren't necessarily good for the organism.
Such as?
Well, you said the ridgeback,
Yep.
because well, we call it a ridgeback because it has that ridge and it looks nice. So we breed that particular trait and characteristic. So all its offspring are going to end up having that ridge.
Fantastic. Okay. And the other thing I want to put into your heads here is we pick for one or two phenotypes really only. We look for a couple of things, we just breed for those. But there are thousands and thousands of genes in every organism. In doing this inbreeding and keeping the breeding within a pedigree, so within a family, we are inadvertently, possibly, this is only possibly, selecting for other alleles that we haven't noticed. For example, I mean, if you think about let's use humans, royal families in Europe, most of them for a time had, was it sickle cell anemia or haemophilia? Haemophilia, which is a genetic disease. They were breeding with each other for being, keeping the bloodline noble, but inadvertently what they did, because it was inbreeding, what they did inadvertently is they ended up selecting for this recessive allele, which gives them haemophilia. So suddenly, to be of royal blood also meant that you were very susceptible to bleeding to death. So inadvertently, they selected for a negative characteristic. We can do that inadvertently. We don't do it on purpose. We can do it inadvertently with anything we selectively breed. We can selectively breed for these fantastic characteristics that make that organism stronger, faster, better suited for the environment we put it in on our farms or in our houses or in our cities or whatever. But without knowing it, we also might choose a family trait, as it were, that is negative, like haemophilia in that example I gave you. So, what I want to do is sum up. Are they really the same thing, or are they actually very different? And that's, think about what we're talking about. They both start the same, they both rely on an external pressure to change a population. The population could change enough that you have new breeds and ultimately maybe even new species. So they have that in common. Natural selection is driven by environmental factors, abiotic and biotic factors. It only selects for those that are best suited for that changing environment, creating, in theory, a stronger population, but also a different population to the original one. Selective breeding, humans select what they want, find the organisms with those, and then breed those ones together to create organisms that suit their needs or wants. In doing so, creating, again, a new breed and ultimately maybe even a new species. So are they different or are they the same?
It's the same process, like in both of them, but I think the main differences between them is, they're different pressures, and the mutations in selective breeding might be negative rather than positive in natural selection.
Good summary. Does anyone have a different point of view they want to add? I think you put that very well. We'll stop there.